afternoon, everyone, and welcome to the 4th Annual Pfizer Colloquium in Statistics at the University of Connecticut. I'm Ted Booth from Economics, one of the many users of statistics represented here. I have the honor of convening this gathering of students and faculty and our most welcome visitors to the campus. It's a great pleasure for me also to welcome one of the grand masters of statistics, our distinguished speaker, Dr. C R Rao. We are indebted to the Pfizer Corporation and the Department of Statistics for bringing us these colloquia. Many of us are from different disciplines and occupations, but all of us appreciate and enjoy these first-hand encounters with eminent statisticians who have contributed so much to our different fields. As an example, I sampled my bookcase for a recent textbook in econometrics, and in the index I counted against the name of C R Rao 9 citations. In that index, Professor Rao, your name is associated with an upper bound. And now to introduce our speaker formally, I present the person most responsible for arranging these events, my friend from statistics, Professor Harry Poston.
Thank you, Professor Booth. Let me add to your welcome my own to all attending our 4th Pfizer Colloquium. These colloquia are sponsored by the Pfizer Central Research, Pfizer Incorporated, and they bring to Connecticut the most distinguished statisticians in the world. Today we are extremely fortunate to have as our guest one of the world's most distinguished statisticians, Dr. C R Rao. Dr. Rao is currently University Professor at the University of Pittsburgh and Jawaharlal Nehru Professor at the Indian Statistical Institute. Because of the importance of this event, we are videotaping the presentation for inclusion in the American Statistical Association's archives. Professor Rao's research career has already extended over a period of 40 years, and it has been a very productive one. He has published over 200 research papers and is the author of 9 texts. 2 of his most famous books, Advanced Statistical Methods in Biometrics Research and Linear Statistical Inference and its Applications, have been used worldwide, the latter having been translated into 5 languages, including German, Russian, and Japanese. One of these books was included in the 1973 listing of 78 most heavily cited works in the area of pure mathematics. And in the same year, the other one was on the list of the 72 most heavily cited works in the area of applied mathematics. This is an indication of Dr. Rao's great range of interests. This breadth, however, makes it difficult to provide a brief summary of his contributions. His publications cover a wide range of areas from mathematics to applied statistics. His applications of statistics to a number of areas such as psychology, anthropometry, genetics, and several other fields have caused a number of individuals to follow his lead in their own fields. His theoretical contributions are difficult to summarize, for he has made a number of major contributions to several areas. In the theory of statistical estimation, he has provided a unified theory of linear estimation. And in the same general area, all graduate students are familiar with the famous Rao-Cramér bound for the variance of an unbiased estimator and with the Rao-Blackwell theorem for conditional variances. He has made numerous contributions in the area of multivariate analysis, including those to dispersion analysis, cluster analysis, and discriminant analysis. His contributions to mathematics in the area of combinatorics and G-inverses have been important to several areas of statistics. These contributions have been widely recognized, and he has been the recipient of many honors. He has been elected a fellow of a number of scientific societies, and he has received honorary doctorate degrees from 6 universities around the world. He has been president of the Institute of Mathematical Statistics, the International Biometric Society, the International Statistical Institute, and the Indian Econometric Society. He has lectured on every continent except Africa and Antarctica, and today he will present to us an important historical talk. The title of his talk is Multivariate Analysis, Some Reminiscences on its Origin and Development. And I am honored to present to you Dr. C R Rao.
Ladies and gentlemen, it gives me great pleasure in thanking the Pfizer Corporation and the Statistics Department of the University of Connecticut, especially Professor Harry Poston, for kindly inviting me a second time to speak at the Pfizer colloquium within a short period of time. I would also like to thank Professor Booth and Professor Poston for the kind words they have said about me. Today, I would like to talk to you about multivariate analysis, the state of the craft as it was when I was a student, and the directions in which it is progressing today. The origin of the multivariate analysis can be traced to the writings of Gauss, Bravais, Scholz, Galton, and Edgeworth during the 19th century. But the key figure whose quest for knowledge on the laws of heredity has triggered off research in multivariate analysis is Francis Galton. In a lecture delivered at the Royal Anthropological Institute in 1885, Galton presented his analysis of data on the heights of parents and adult children in the form of a bivariate frequency chart as shown in figure 1. He made the following observations. The locus of verticals, that's what he calls the graph joining the conditional mean heights of children given parents' height, is nearly a straight line. Now the scatter of points is homoscedastic, that is the conditional variance of children's height given parents' height is the same for all parental heights. The equiprobable contours of the bivariate distribution are elliptical. Having noted these three properties, namely linearity of regression, homoscedasticity, and an elliptic form of the equiprobable contours, Galton could have written down the expression for the underlying distribution as bivariate normal. It is surprising that he did not. However, he mentioned these properties to a Cambridge mathematician by name J.D. Hamilton Dixon, who immediately gave the right answer. The bivariate normal distribution is one of the noteworthy scientific discoveries arising from very simple and pure analysis of observations. Having found the expression for the bivariate normal distribution, the generalization to the multivariate case was only a simple step. Galton also found some very interesting features of his analysis of heights of parents and their children. From the locus of verticals, which we now call a regression line, he inferred the phenomenon of reversion, which was later referred to as regression, namely the tendency of the conditional means at the extreme values of parental heights to depart from the parental type and revert to the general mean. He introduced a numerical measure, or to quantify the magnitude of reversion. Now this R is the source of our symbol for the correlation coefficient, which according to Carl Pearson was really the first letter of reversion. Galton's work and its relation to the bivariate normal distribution won 3 recruits for the field of correlation. 3 famous names, Weldon, Edgeworth, and Carl Pearson. Galton himself called his measure, or the index of correlation, which was changed to the more weighty word coefficient of correlation by Edgeworth, while Weldon, who computed the values of R for a number of bivariate samples, called it the Galton function. Weldon and Edgeworth did considerable spade work, which was followed by Carl Pearson and Shepard, the Shepard who has given us corrections for the movements. They worked out the expression for the partial, multiple, and total correlations as we know them today, and also provided the large sample standard error of the correlation coefficient R. All this work was done before the end of the last century. It was recognized that the distribution of R was Q, and for purpose of inference in small and even moderately large samples, its exact distribution was necessary. All efforts to find a breakthrough failed until 1915, when R. A. Fisher emerged on the scene and gave us the exact sampling distribution of R. This famous paper marks the beginning of research in multivariate analysis as a statistical technique for drawing inferences from multivariate data. The form in which the exact distribution of R was expressed was somewhat complicated, but Fisher very soon found an elegant transformation from R to R equal to hyperbolic tan Z, which is popularly called the Z transformation of Fisher. Now this considerably simplified the distribution of R and the inference procedures based on an observed value of R. In the early 20s, Fisher also introduced the F distribution, which provided the tests of null hypothesis for regression coefficients, partial, and the multiple correlation coefficient. During this period, Fisher also introduced the method of maximum likelihood of estimation and developed the modern technique of the design of an analysis of experiments. The book Statistical Methods for Research Workers by R. A. Fisher, first published in 1925, was essentially a practical handbook on these new methods. This book opened up the doors to new knowledge through appropriate analysis of data and soon became popular, especially with biologists who are amassing masses of data. Perhaps the main drawback of this book from the modern point of view is its heavy emphasis on tests of null hypothesis and the use of the 5% and 1% levels of significance. I must add that Fisher himself did not religiously use the 5% and 1% levels of significance in his own work. But in his wisdom, he must have thought that some sort of safe prescription would be needed for practical workers in interpreting an observed value of a criterion, as for instance contradicting a null hypothesis or not. This was useful especially because the entire cumulative probability distribution could not be provided to research workers. So he thought at least the percentage points corresponding to the 5% and 1% level might be of some use. Fisher's 1925 book attracted the attention of research workers from all over the world. The next 10 years saw some major advances in multivariate analysis, mostly under his guidance. In 1928, Wishart extended Fisher's work on the bivariate normal distribution to the general p-variate normal distribution by finding the joint distribution of the estimated variances and covariances. Hotelling from the United States introduced his capital T-square statistic in 1931 as a generalization of students T to the multivariate case. Hotelling also developed the concepts of principal components in 1933 and canonical correlations in 1936. Wilkes, again from the United States, started in 1932 his work on likelihood ratio criteria for testing various hypotheses concerning the mean vectors and covariance matrices of multivariate normal distributions. At the suggestion of Fisher, Martin constructed in 1936 the well-known linear discriminant function for deciding whether a jawbone found in a grave belonged to a male or a female. Fairfield Smith, who was attached to this university for a period of 10 years, worked out in the same year, that is in 1936, what is called the discriminant function for plant selection, which is, I would like to emphasize, the forerunner of what is now known as empirical Bayes estimation. This was in 1936. While Hotelling and Wilkes in the United States were interested in tests of significance, Mahalanobis in India was concerned with the problem of studying interrelationships among a given set of populations. For this purpose, he devised a measure of distance between two populations known as Mahalanobis d square, which appeared to be an improvement over Pearson's c square, the coefficient of racial likeness. In 1938, Bose and Roy found the non-null distribution of Mahalanobis D square, which has the same form as that of the multiple correlation derived 10 years earlier by Ore Fisher. The analogy was not clear why these two statistics should have the same distribution until Bowker found in 1966 an elegant representation of the D-square statistic as the ratio of two independent chi-squares, one of which has a non-central distribution. Fisher used geometrical arguments in deriving the distribution of the multiple correlation coefficient, and people did not understand how he arrived at the final results because many of the intermediate steps in the argument were missing. This is usual with Fisher's writings. Mahalanobis, in his biographical sketch of Fisher, mentions that Fisher does not attempt to write down the analysis until the problem is solved in his mind, and sometimes he confesses after the key to the solution has been forgotten. Fisher generalized the discriminant function approach to more than two populations, which led to the sampling theory of what are called roots of determinantal equations, which are the same as the eigenvalues of one random matrix with respect to another independent random matrix, both having a Wishart distribution. Fisher found the exact null distribution of these roots in 1939, which is his last major work in deriving sampling distributions. The distribution has the same form in the null case as that of the test criteria introduced by Roy in the same year for testing equality of two covariance matrices. These are the main lines of development in multivariate analysis up to 1940. I must also mention that there were other types of studies involving multiple measurements, such as factor analysis. Sometimes it was given a fancy title such as the vectors of the mind. This originated with Spearman in the beginning of the century, but did not receive much attention from the statisticians. This might be partly due to the difficulties involved in estimating the large number of unknown parameters in a factor analytic model, and partly to the subjective interpretation and doubtful utility of the results arising out of factor analysis. There were no references to any existing factor analytic methods in Fisher's own writings, although he postulated a factor analytic model to explain the variations of human measurements in his famous paper on the correlation between relatives published in 1918. Unlike the fact analysts, Fisher was cautious in making the distinction between the actual number of factors and the effective number of factors, and he thought that the latter, though abstract, had a conceptual meaning and might be estimable. In 1940, I graduated in mathematics with statistics as a special subject. The job opportunities for a mathematician were very poor during the wartime. There were not enough scholarships for pursuing a research career in mathematics. After remaining unemployed for about 6 months, I had to choose between joining the British Army or going for an alternative course of study which provided better prospects. I had heard about the Indian Statistical Institute, which was established by Mahalanobis a few years earlier. Mahalanobis was at that time trying to lure all intelligent students to study the new subject of statistics, promising them an attractive career. I felt extremely happy when, in response to my application, he admitted me to what was called the training section of the Indian Statistical Institute to be trained as a statistician. This was at the beginning of the year 1940, which turned out to be the beginning of my career as a statistician and my long association with the Indian Statistical Institute, which continues even today. Soon after joining the institute, I met Bose, Roy, and Mahalanobis. Bose was working on combinatorial problems in design of experiments. Roy was continuing his work on the roots of determinantal equations, and Mahalanobis was developing the theory and methodology of large-scale sample surveys. As a part of my training in statistics, Mahalanobis, who always emphasized the difference between statistical education and statistical training, assigned me to an anthropometric project. I was to be in charge of the analysis of about 12 morphological measurements made on a large number of individuals classified by about 21 caste groups and tribes in India. In this study, I was supposed to use Mahalanobis D-square as the main tool. This meant computing a large order covariance matrix, finding its inverse, and computing a number of quadratic forms, because Mahalanobis D-square is a quadratic form. This, as you may realize, is an impossible task at the time when we had only the mechanical desk calculators. My first problem was therefore to devise methods for reducing the number of measurements just to simplify the computations. Now this needed a criterion for selection of variables. As a first step in this process, I derived a test criterion called capital VR for testing the equality of means of several populations. VR is nothing but the weighted average of all possible D-square values based on our specified measurements for different pairs of populations. The distribution of VR where the variance covariance matrix was known or was estimated at a large number of degrees of freedom was reported in my master's degree thesis in 1943 and later published as a note in 1945. The statistic VR, which I called the perimeter test because it is sum of all possible D-squares, is now known as the trace criterion, being the sum of the roots of the determinantal equation of Fisher. I used the same test criterion by taking a simple average of all possible D-square values for the selection of our best variables by maximizing VR over all possible selections of our characters out of P. This was still a difficult problem for the desk calculator, and some shortcuts had to be made instead of computing all possible VR values. I am glad to see that this procedure is now available in a computer program for the selection of variables in discriminant analysis. I wanted to make sure that not much information is lost by reducing the number of measurements. To examine this, I derived a criterion for testing the significance of the extra information gained by augmenting a specified set by an additional set of measurements. This criterion, which was described in a paper published in Sankhya in 1946, also provided a generalization of the Fisher-Bartlett's test for an assigned discriminant function. For instance, we can test whether the coefficients of a true discriminant function lie in any specified subspace. To avoid the inversion of a large order covariance matrix, I used a stepwise transformation of the correlated variables into uncorrelated set and compute D-square as a sum of squares. The transformation was carried out in a triangular scheme listing all the measurements in order of their importance in discrimination. Later I discovered that the method of transformation I used is the well-known Gram-Schmidt orthogonalization process, and the method of computation employed is numerically a stable one for which computer programs exist. Following the work of Fisher and Roy on the roots of determinantal equations, I introduced in a paper published in 1945 what are called familial correlations, which are generalized intra-class correlation coefficients obtained by considering linear combinations of measurements. With multiple measurements on each of k brothers or sisters in several families, the familial correlations are functions of the eigenvalues of between to within family covariance matrices as in Fisher's problem. They have the same definition and null distribution as Fisher's statistics, but their non-null distribution is similar to that of Roy's statistics. They also provide a specialization of Hotelink's canonical correlations when we use the same linear combinations of coefficients for the two sets of measurements as we have on brothers. In the course of my 2 years' work on anthropometric data at Calcutta, I was able to establish credentials of my expertise in multivariate analysis. This I realized when Mahalanobis decided to send me to Cambridge, England, in response to a request from J.C. Trevor, an anthropologist at Cambridge, to depute someone to apply Mahalanobis d-square on some skeletal data collected by a British expedition from a place called Jebel Maya in Africa. I arrived in Cambridge in the fall of 1946 and joined the Duckworth Laboratory, which housed the Anthropological Museum. Although I was theoretically oriented and would have preferred to work in a cleaner place and not in the midst of bones and stones, I took my new assignment as a challenge and settled down to work, this time with an electric desk calculator as my companion. My visit to Cambridge was profitable in many ways. Although Fisher had earlier written a paper criticizing Carl Pearson's C-square, the coefficient of racial likeness, and denouncing all research work on skeletal material as futile, he agreed to be my supervisor for a possible PhD thesis arising out of my work on the skeletons. He was happy to see some extensions of his work I was making on the discriminant function when more than 2 populations were involved, but thought that it would do me good to spend some time in his mice laboratory where work was being done on the mapping of chromosomes of mice. So I ended up working at both places, in the Duckworth Laboratory where I was handling bones of dead people, and Fisher's laboratory at Whittingham Lodge where I was experimenting with living mice, weighting different types and studying the progeny. In the case of the African material, all the measurements were made by the British anthropologists at the site of the excavation, and only a small portion of the bones, those that were well preserved, were shipped to the museum at Cambridge. By the time I reached Cambridge, the measurements were already processed on the IBM machines. For instance, the means and standard deviations were computed for each character after classifying the bones by 3 levels of depth from which they were excavated. While working on the anthropometric material in Calcutta, I became deeply aware of the existence of recording errors, investigated differences, and outliers in any large body of data collected under field conditions. I therefore decided to set aside the nice IBM printouts and look at the original schedules for possible errors. Scrutiny of data, or to use a more appropriate expression due to Fisher, cross-examination of data, is not a routine type of work. A statistician has to look for gross irregularities in the data due to presence of outliers and errors of various kinds, and also noticeable regularities due to faking. Thus, it may be necessary to subject the data to what may be called an irregularity analysis to detect errors and a regularity analysis to detect faking. An example of the latter kind of analysis is that of Mendel's data on suite P by Fisher, which indicated that Mendel's data were possibly adjusted to agree closely with expected values. In scrutinizing multivariate data, it always pays to examine the distributions of individual measurements and ratios, plot the histograms, compute the first 4 moments and measures of skewness and kurtosis, and examine the changes that take place in these descriptive constants when the extreme values are omitted. Now, table 2, which is figure 2, provides an example of such a procedure where the figures marked in red are high values of skewness and kurtosis computed from the original data. Now, the recomputed values, after omitting white outliers, are in conformity with others. So this, I believe, is a very simple method of detecting outliers and also examining when these outliers are omitted whether the rest of the data are in conformity with data of similar kind. Plotting of principal components or simple bivariate frequency charts can also be of great help in detecting errors and outliers. Such examination of the original data on the African material led to discarding the whole of the field data and working only with the measurements made at the laboratory on a small sample of material sent from the excavation sites. Another difficulty faced was a high degree of incompleteness of the data. Most of the skulls are broken, and not all measurements could be taken on every skull. For instance, cranial capacity could be measured only when the whole skull was intact. How does one estimate the mean values and variance and covariances when data are incomplete? I am surprised to see some recent papers on this subject where maximum likelihood estimates and likelihood ratio criteria are recommended on the assumption that the missing values occur in a random manner. This is not generally true in practical problems. For instance, the skulls that were well preserved were found to be on the whole smaller in size than those that were broken. Now this showed that the sample of well preserved skulls cannot be a representative sample of the original population of skulls. Thus, pushing all the data through the likelihood mill might give wrong results. Suitable adjustments had to be made in arriving at plausible estimates of the parameters characterizing the original population of skulls. When I found this phenomenon of differential preservation of skulls in the graves, I thought it was an interesting result. So I took the first opportunity of talking about it at a conference of statisticians. I showed by very careful statistical analysis of several series of skeletal data that a small skull has a greater chance of being preserved than a large skull in a grave. At the end of the talk, the chairman of the meeting wanted to make some comments. He said he was taking a guided tour of a museum in Paris along with some tourists. The guide stopped near a glass case and said, "The well-preserved skull you see in this glass case was Caesar's." Everybody looked at it with great wonder that they were looking at Caesar's skull. Now one person among the tourists, who obviously read about Rao's discovery, said that Caesar had such a small skull, no wonder it was well preserved. Now the guide said, actually, this was Caesar's skull when he was 16. The next problem was the use and interpretation of the computed d-square values between the groups under comparison. Cluster analysis algorithms were not developed at the time in 1946. However, one could attempt to roughly indicate the relative positions of the various groups on a two-dimensional chart using the d-square values. I tried to make such a representation more objective through what I have called canonical variates, which are ordered linear combinations L1, L2 of the measurements, such that the first k of them, say L1, L2, Lk, provide the best representation of the groups in a k-dimensional subspace of the space of all measurements. Now these linear combinations are computed using the eigenvectors of the variance covariance matrix between groups relative to within, as shown in a paper published in the Journal of the Royal Statistical Society in 1948. Now figure 3 is an example of such a representation based on the first two canonical variates. The points you see represent the groups, represent some castes in one of the states of India. In practice, one could make a three-dimensional model using the first three canonical variates or a series of three-dimensional models from a selected set of canonical variates. It should always be borne in mind that there will be some distortion in representing higher dimensional data in a space of lower dimensions. To guard against this, it is necessary to compute the amount of distortion caused in each distance between groups and use this knowledge in interpreting the configuration of points in a 2 or 3-dimensional model. Following the work of Torgerson on multidimensional scaling, I suggested in a paper in 1964 a method of computing canonical variates directly from a table of d-square values, or, as a matter of fact, any dissimilarity measure estimating the underlying distances. I am glad to see that such graphical representations through canonical variates or coordinates are now widely used, although the caution I have indicated regarding the distortion of distances is not usually considered. I prefer the mnemonic can-coord for my canonical variates, which sounds less guilty than CRIM coordinates suggested by Gnanadesikan. Since the 50s, many methods of cluster analysis have been developed, and there are several books describing various algorithms for cluster analysis. However, I still believe what I have stated in an early publication, that no specific rules can be laid down for forming clusters. Different methods may have to be used in different situations. For instance, it is possible that number of groups may form a chain with each group closely linked to 2 others. In such a case, forcing the groups into a distinct clusters or a tree pattern may lead to wrong interpretations. I have advocated listing of clusters of groups which may be overlapping, such that the groups within a cluster have dissimilarity coefficients less than some chosen value. Such a listing can be pictorially represented as a graph with subgraphs as shown in figure 4. Now in figure 4, the vertices represents the groups, and all vertices with distances less than a chosen threshold value are connected. Now such a figure has more information than, for instance, a dendrogram. Now from a dendrogram, we could not have inferred that the group My has a very central position in the configuration of the various groups. Now this observation from a picture of this kind has led to an interpretation of the relationship of My with other groups consistent with historical facts. Bartlett was making valuable contributions to multivariate analysis during and immediately after the Second World War. In 1947, he read a paper at a meeting of the Royal Statistical Society summarizing his work. I had the opportunity to attend this meeting and participate in the discussion. In his paper, Bartlett derived tests of some hypothesis by factorizing Wilks' overall lambda criterion, about which I had some doubts. The resulting test procedures seemed to underestimate significance. I made some remarks at the meeting based on the work I had been doing at the time. My paper, published in Biometrica in 1948, clarified some points in Bartlett's paper. It also provided a general framework through what I called analysis of dispersion, a term approved by Fisher but later christened as MANOVA in the US, for testing specified hypotheses such as main effects, interactions, effect of regression, deviation from regression, effectiveness of concomitant variables, and additional information contained in some measurements in problems of discrimination. During my student days, Fisher's Statistical Methods was the only book on statistics, advanced book on statistics, but it was neither prescribed in the text nor recommended for general reading. It is not an easy book to read for those who want to understand the basics of statistical methodology, as the proofs and assumptions under which various results are derived are not clearly set out. I have even heard remarks such as, "You should not attempt to read it unless you have read it before." However, I found Fisher's book very stimulating, and wrestling through it was indeed a rewarding experience. I had even organized a study circle to read every page of Fisher's book and discuss its theoretical and practical contents. It occurred to me that it was worthwhile to write a commentary on Fisher's book, supplying the missing theory and mathematics and expanding on what I thought was its tour de force, analysis and interpretation of small, self-contained sets of data. My work in Calcutta and Cambridge on anthropometric data provided excellent material to review Fisher's methods and also discuss the multivariate statistical methodology not covered in Fisher's book. I was also looking for an opportunity to put together the contributions of the Indian School of Statisticians to multivariate analysis for wider dissemination. I started writing the book while I was still in Cambridge. I could not decide on the title for a long time. The book had enough theory and mathematics to be called mathematical statistics. This would have probably attracted a wider attention, but being somewhat mission-oriented at the younger age, I wanted to emphasize the practical aspects of statistics and so decided to call it Advanced Statistical Methods in Biometric Research. I returned to Calcutta from Cambridge with a PhD degree and a first draft of Advanced Statistical Methods in Biometric Research, and with a reinforced conviction that contact with live problems is essential for worthwhile research in statistical methodology. Now to talk about the modern trends of research in multivariate analysis. The course of research in multivariate analysis followed in two different directions during the last 25 years. In one direction, there has been vigorous work by Anderson, James, Pillai, and others in determining the exact distribution of roots of determinantal equations in the non-null case, devising various test criteria based on them, and constructing tables of percentage points for carrying out tests of null hypothesis. In multivariate analysis, one is often led to consider several hypotheses or estimate several parameters simultaneously. Appropriate inference procedures necessary in such cases are being worked out under the assumption of normality by Krishnaya and his colleagues. In another direction, breaking away from the dependence on the multivariate normal distribution and probability considerations, Kendall, Kruskal, and their colleagues are solving interesting problems such as seriation of archaeological material, constructing evolutionary tree structures in historical and other contexts, and multidimensional scaling. Cavallis-Froza and Ney are estimating tree structures of biological evolution using genetic models. Research in multivariate analysis is still in a growing stage. There are numerous problems for which we have no answers or which are not satisfactorily solved for practical applications. I am reminded of what Finney once said, that research in multivariate analysis has served only as outlets for mathematical skills of authors without any practical use. And the skepticism expressed by Tukey that we go multivariate when we do not understand the situation. I hope this will change if future research workers address themselves to the solution of problems arising out of practical applications. I must also refer to the uncritical use of computer package programs. Unfortunately, the tendency has been to let a computer program decide the questions to be raised in any particular problem and solve them in a particular way. Now take for instance the problem of deciding whether Australopithecus africanus, a fossil tooth discovered in Africa, is hominid or anthropoid. Now since it appeared to be a problem of discrimination between two populations, the appropriate computer program for discriminant analysis was chosen. Now the computer printout gave the categorical answer that the fossil is more likely to be a hominid than anthropoid. In fact, it can be seen from figure 5 that the observed fossil does not fit in with either hominid or anthropoid samples. The possibility that the specimen to be classified may not belong to any of the specified groups was not considered. Now this led to the computation of Mahalanobis d-square values of the observed fossil, not from its actual position as you see there, but from its projection p in the direction of the discriminant function. Thus we find from figure 5 that its d-square value from the human is 0.3, which is smaller than the d-square value 3.8 from the chimpanzee. Now this led to the wrong conclusion. I would like to say that there cannot be tailor-made computer programs for every problem, but the ready-made loose fits can be of great help in determining the shape of the final analysis. I must also refer to graphical methods which are being developed to provide a better comprehension of the underlying structure of multiple measurements, to detect outliers, and to help in the interpretation of statistical results. Reference may be made to a recent book on this subject by Gnanadesikan and the pictorial representation of multivariate data suggested by Chernoff. I would like to thank you for your patience in listening to my reminiscences and personal comments on certain aspects of the developments in multivariate analysis.
Thank you, Dr. Rao. On behalf of your present audience and your future audiences who will view this videotape, let me express our gratitude to you for a stimulating view of the beginnings of multivariate analysis. We are most appreciative. This concludes our fourth Pfizer colloquium.